In this class, we will discuss a problem of a cantilever beam examination question paper problem, January 2020 VTU, to find the support reactions. As you know, cantilever beam has got only one support, that is a fixed support. Here A is the fixed support, and at the other end it is free. There is no support at the other end. So, by the characteristics of a fixed support, it has got generally three reactions. One reaction in the horizontal direction, another reaction in the vertical direction, and also a resisting moment. So there will be fixity there. There will not be any rotation or translation at a fixed support. So generally, we will be having three reactions: HA, VA, and MA. So initially, you can assume a certain direction for those reactions. Later, after the analysis, if you get positive values for those reactions, the assumed direction is correct. If you get negative values, then it is in the opposite direction. Now here AC is the cantilever beam, which is subjected to three loads here. One is inclined concentrated load 30 kN at angle 60 degrees with the horizontal. Another one is UDL of intensity 10 kN over a length of 2 meters. And one more anti-clockwise couple is acting, external couple or external moment is acting 12 kN at the point C. Of course, the effect of that 12 kN remains the same whether it acts at C or B or at A at any point, because as you know from the characteristics of a couple, the effect of a couple remains same at the through any point in the plane. Now that means you have three reactions here in general at the support A, and you have no reaction at B. So HA, VA, MA, they are the three reactions. So let me take HA like this, VA like this, and MA like this. You can assume any direction initially. Now, of course, since you have three reactions, you have given three equilibrium equations. So three equilibrium equations have sigma Fn0, sigma Fy0, sigma Ma0 or sigma Mc0. At any point, algebraism of the moments has to be 0 for equilibrium. Oh, that means I will take the first, before using the equilibrium equation, we have to write the free body diagram of the beam. So as you know, free body diagram is written by transforming the loads in terms of equivalent concentrated loads, and also by replacing the support by the respective reactions. Now the PD of the beam AC will be like this now, A, B, C. So I have to show these reactions HA, VA and MA. Then I have to write the forces acting. Of course here I have to resolve this 30 kN because it is inclined. So at B you have a horizontal component like this and vertical component like this. Please note that the arrows of these two component forces should meet the arrow of the inclined force. Now since 60 degrees is the angle with respect to horizontal, so this horizontal load will be 30 cos 60 and the vertical load will be 30 sin 60. Next, coming to UDL, you have to convert this UDL to equivalent concentrated load. The concentrated load is intensity multiplied by distance. So 10 into 2, 20 kN, which acts at the midpoint. So midpoint I will take as B here. So 10 into 2 is the concentrated load, equivalent concentrated load, 20 kN. Now this, of course, this 12 kN anti-clockwise couple remains same. So this is the free body diagram. Of course, distances are very important because we have to calculate the moments. So this is 2 meters, this is 1 meter, this is also 1 meter. So now this is the free body diagram of the cantilever beam. Now let us apply the equilibrium equations. First equation I will take sigma Fn0, forces acting towards right positive, left negative. Now here I have taken HA in the towards right direction, so it is positive. And of course this 30 cos 60 is also acting towards right, therefore that is plus is equal to 0. So therefore HA you are going to get negative minus 15 because cos 60 is half. So half into 130 is 50. So when you bring that side, it becomes minus. This minus indicates that HA acts in the towards left now. That is the mean. So the negative value you have got, that means your assumed direction is wrong. So reaction acts in the other direction. So HA will be like this. Then the second equilibrium equation is sigma F by 0. Upward force is positive, downward force is negative. So if you see the diagram, only VI is the upward force, so it is positive. 30 sin 60 is negative because it is downwards. Then 20 is negative. So please note that you should not consider this couple or moment, external moment when you are using sigma F by 0, sigma F by 0 equation. Now simplify this, you will get VA. So VA is 30 into sin 60 plus 20. So if you simplify that, 30 into sin 60 plus 20, so it becomes 45.98 kilonewton. So you have a positive value, that means the assumed direction of VA is correct, that is upwards. Now once you get these two, you can find out the resultant reaction RA also. Resultant reaction is given by square root of HA square plus VA square, that is minus 15 square plus 45.98 square, which is equal to, so minus 15 square plus 45.98 square under root. So it comes out to be 48.36 kilonewton, and the direction of that will be, since HA is acting towards left, and VA is acting upwards like this. So definitely the resultant reaction RA will lie in the second quadrant. That means it will be acting like this. So this is the direction of RA, and if I take this angle as alpha, alpha is tan inverse of VA by HA modulus. So which is nothing but tan inverse of 45.98 divided by 15. So it comes out to be, angle is, so 45.98 divided by 15. So tan inverse of that 71.93 degrees. 71.93 degrees, that is the value of alpha, angle made by resultant reaction RA with the horizontal. Now this is one thing. Now we have to find out the resisting moment also. Resisting moment I have taken it as MA. So to find that, I will use the third equilibrium equation. Sigma MA is equal to 0, clockwise positive, anti-clockwise negative. That is my convention. Now you can see that here this MA is diagonal in the anti-clockwise direction, therefore it becomes minus MA. And moment due to this 30 cos 60 will not be there, because if you extend the line of action of this 30 cos 60, it passes through point A. Therefore, moment of that force about the point A is 0. But this 30 sin 60 is giving a clockwise moment about A. So it is plus 30 sin 60 multiplied by distance of the 30 sin 60 force from the point A, perpendicular distance, which is 2 meters. So into 2. Next, coming to this 20 kilonewton, it is also giving a clockwise moment. So plus 20 into distance is 3 meters. Plus 20 into 3. Next, this 12 kilonewton meter, it is an external moment or couple given. It is anti-clockwise, so minus 12. Don't multiply by the distance. So wherever it acts, this 12 kilonewton, whether here or here or here, its effect is same. Therefore, you should not multiply by the distance. So just you have to take 12 with negative sign because it is anti-clockwise. Suppose if it is clockwise, we have to write plus 1. So this is equal to 0. So this is the moment equation. Now MA, if you want, MA will be equal to, I will bring this MA to RHS, it becomes positive. So only LHS I have to simplify. 30 sin 60 into 2 means 60 into sin 60. So 60 into sin 60. Then you have plus 20 into 3 is 60, then minus 12. So it comes out to be 99.96 kilonewton meter. 96 kilonewton meter. That is the unit of the moment, because the force is in kilonewton, distance is in meters. Kilonewton meter, you have got positive value. Be careful here, you have got positive value here. Since you have got positive value, your assumed direction of MA is correct. So it is anti-clockwise. So this is how we have to get it. So HA is towards left, VA is upwards, MA is anti-clockwise. Now, if you want to show that in a diagram, so at A you have two reactions, but one horizontal and vertical, that can be replaced by a reaction like this RA. So direction is in second quadrant, because HA is negative, VA is positive, and this is your alpha. So alpha value is you have got 71.93 degree, whereas HA value, reaction value is 48.36 kilonewton. And at C, here you don't have any reaction. In addition to this RA, you have an anti-clockwise reactive moment of MA, which is equal to 99.96 kilonewton. So this is how we can represent the reactions in the cantilever beam. So we have got HA is equal to minus 15. That means minus 15 means you have it is acting towards left. VA is 45.98, which is positive, means it is upwards. Then RA, second quadrant, 48.36. So second quadrant. Then you have alpha, angle made by RA with horizontal, 71.93 degrees. Then you have reactive moment MA anti-clockwise, 99.96. Please once again you check the values. So this is an examination problem. I will take another problem that is also in the same paper. It is given in the same paper. So let us see how the problem is given and how it is solved. So second problem in the same question paper. So the problem is given like this. This is an overhanging beam. Overhanging beam, something like this. So you have a hinge support here and a roller support here. Hinge and roller. It is subjected to UDL over a length of 4 meters. This UDL is 10 kilonewton per meter, intensity is given, over a length of 4 meters. See, this length of UDL is 4 meters, and then you have another here you have a clockwise couple, external couple, 70 kilonewton meter, and this distance is 2 meters, and another he has given a UDL from this in the overhang portion. So this is the overhang portion. This UDL is 16 kilonewton per meter. Of course, the overall length of 2 meters. So total length of the beam is 10 meters. From here to here. So if I take this as AB, this is CD, and this is E. Okay, so from A to C, you have UDL 10 kilonewton per meter over length of 4 meters, and at D you have an external couple, clockwise couple 70 kilonewton meter. B is a roller support from B to E. This is the overhang portion. The portion beyond the support is called as overhang. It is singly overhang. So this side there is no overhang. Singly overhanging beam. So suppose the overhang is there, this side also, it is called as double overhanging beam. Now we have to find the support reactions for this. So as you know, the hinge end we have generally two reactions, one horizontal, one vertical, and at roller end we have only one reaction. But here, if you observe the diagram, there are no inclined forces, there are no horizontal forces. If inclined force is there, then only you will add the horizontal component of the inclined force. Since here in this problem there is no inclined force given on the beam, it doesn't have any horizontal reaction. So only if inclined force is given, horizontal reaction will be there, or if there is any horizontal load is given, then only horizontal reaction will develop. In this case, this problem, AC is UDL vertical, BE also it is UDL vertical, and this is external moment. So therefore, this problem there is no horizontal load or inclined load. So since there is no horizontal load or inclined load, so no horizontal reaction. So there is one important thing. So even though A is a hinged support, you have the value of HA as 0 here because there is no horizontal load or inclined load. So therefore, one reaction is not there. We have only two reactions. So those two reactions are RA and RB. So only two reactions we have. So you are not using the first equilibrium equation sigma Fx 0. You are using only sigma Fy 0 and sigma Ma 0 for analyzing the problem. So using these two, we can find out RA and RB. Here in this problem, since HA is 0, this RA itself is given VA. Okay, now we will write the free body diagram of the beam. To draw the free body diagram of the beam, we have to transform or convert that UDL into equivalent concentrated load, and we have to replace the supports by the respective reactions. Then we get the free body diagram of the beam. Let us draw the free body diagram of the beam now. So ACDBE is the beam. Okay. So A is here, C is here, B is here, then E is there, that side. So A is here, D, then B, like this. Okay. Distances are very, very important. So at A, remove the support replaced by a reaction RA. So here please note that HA is not here because there is no horizontal load. And at B you have RB like this. So two reactions are there. Now convert this UDL to concentrated load 10 into 440, which acts at the midpoint. So midpoint I will take it as F here. So 10 into 440 kilonewton is the concentrated load, equivalent concentrated load acting at the midpoint. That midpoint I have taken as F. Then you have this at D, you have a clockwise, external clockwise couple or moment, you write as it is 70. Then from B to you have UDL, total load will be 16 into 2, 32, which acts at the midpoint of BE. Midpoint of BE, I will take it as D here, next alphabet. So 16 into 2, 32 kilometers. Now I will write the distances now. Distances it will be correctly, it should correctly write because we are taking moments. So please note the distances here. So from A to F, half of 4 meters, that is 2 meters, and this is from F to C, it is 2 meters. Once again, C to D is 2 meters, then D to B is 2 meters, then B to D is 1 meter, half of 2 meters, and this is 1 meter. So total length of the beam here is 10 meters. So if you add this, you should get 10. Now this is the free body diagram of the beam, the BD of beam. Now we will use only two equilibrium equations because HA is 0. There is no need to use sigma Fx is equal to 0. Only two equations. The first one is sigma Fy is equal to 0. Upward positive, downward negative. So here upward forces are the reactions RA and RB, both are positive, others are negative. Minus 40, minus 32. So don't write the 70 kN when you are using the force equation. So that is sigma Fx 0, sigma Fy 0 when you are using. You should not consider the external couple acting on the beam. Only forces we have to take. This is equal to 0, or I can write RA plus RB is equal to 72. So this is the first equation. You cannot solve this because there are two unknowns. Second equation is sigma Ma 0, clockwise positive, anti-clockwise negative. That is the convention we have to use. So now I am here to calculate the moments of all these forces. So only I have to take the moment of this and these two. So about the point A, so it is giving clockwise. So 40 into 2. So 40 into 2 clockwise is positive. Of course, this RA doesn't have any moment about it because the line of action of RA passes through A. Then this 70 we have to take as it is. As it is, so plus 70 because it is clockwise. Don't multiply by the distance because its effect remains same wherever it acts. So always please remember that moment value should not be multiplied by the distance. Wherever you take the moment, the 70 remains same. Then this RB is given anti-clockwise moment minus RB. If the distance from point A is 8 meters, okay, it is 8 meters. You can see here it is 8 meters. Then 32 km is giving a clockwise moment, so plus 32 into 9 meters, 8 plus 1 9. So we have to measure the distances from the point where we are taking the moment. Here I am taking the moment at A, therefore I have to measure the distance from A. So from this equation, you get 8 into RB. So just simplify that. 8 RB if you bring to the RHS, it becomes positive. So only I have to simplify this. So it is 80 plus 70, 150. So 150 plus 32 into 9. 32 into 9. So it becomes 438. So 8 RB is equal to 438. Therefore, RB is equal to 438 divided by 8, which comes out to be 54.75. 54.75 kilonewton. Positive value got, that means your assumed direction RB upwards is correct. Now substitute this value of RB in first equation to get RA. Substituting for RB in 1. So you can get the another reaction RA. So RA is 72 minus 54.75. So which is you will get 20.25. 20.25 kilonewton. This is also positive. That means your assumed direction of RA is also correct, upwards. So please note that here RA is less than RB. The reason I have told in the last problem also. So near the point B, support B, we have more loads acting, whereas at point near the point support A, there are much loads. Therefore, the reaction will be more at the support, which is subjected to more load. So that means near that support, if you have more intensity of load, definitely the reaction will be higher at that support. Now, once you get RA and RB, you can represent them by in a diagram. So you have A here, you have C here, you have B here, you have D here, and you have B here. Now, only at A and at B, you have to show only two reactions. RA is this value, which is 20.25 kilonewton acting upwards, and our RB is this value, which is 54.75 kilonewton acting upwards. So the check is, if you add these two reactions, it should be equal to the total load acting on the beam. That means 40 plus 32, 72. So if you add these two values, 72 minus 54.75. Is it not? What is the value? 72 minus 54.75. 17.25. Sorry. 17.25. This one. 17.25. Please be careful here. And of course, this value is 54.75. So the sum of the reactions should be equal to sum of the forces. So action and reaction are equal and opposite, So this is the answer you are going to get. So 54.75 plus 17.25 is equal to 72. So this is how you can represent the reactions in the diagram.